There are two ways to represent a vector. First, let's recap what is and is not a vector. Scalars are quantities that can be represented by a single number. And all of these are examples. If you're in one dimension, pretty much everything is a scalar. You only need one number to represent anything. These others are all examples of scalars. There are other scalars besides these, many more. These are just some that you'll be encountering this year. Vectors, on the other hand, require two numbers to fully represent them. And examples of those are included in 2 dimensions: position, displacement, velocity, acceleration, and soon we'll be getting to some of these others throughout the year. So in this video, I'm going to talk about some general properties of vectors that apply to all of these types of vectors. Okay, so with those 2 numbers that represent a vector, we have 2 different ways to represent them. And of course, they are based on 2 different arcade games, Atari games, Pac-Man and Asteroids. The first way to represent a vector, Pac-Man style, is in terms of its components. When Pac-Man wants to get from point A to point B, he moves to the right, and then he takes a 90-degree turn, and he moves up. So first he moves in the X direction, then he moves in the Y direction. And he only makes those right-hand 90-degree turns. In Asteroids, on the other hand, your spacecraft is able to rotate 360 degrees, point itself in the direction it wants to travel, and then travel directly along that path. So it gets to choose an angle and then a distance it wants to travel. The angle corresponds to the direction of the vector, and the distance it travels in that direction corresponds to the magnitude of the vector. So here is the same vector. We'll call it A. There's our little harpoon over the A indicating that it is a vector. The same vector, we can tell that it's the same because it has the same length and it's pointed in the same direction, pointing that way, pointing that way. So it's the same vector, but we're going to represent it 2 different ways. Here, Pac-Man style, we're going to represent it with its components. The leg of this triangle, a right triangle that we can draw, the leg parallel to the x-axis, that represents the x component of the vector. We call it a sub x. And the leg parallel to the y-axis, we call it the y component of the vector, a sub y. And I'm saying that this has a value of 4 units, this 3 units. I'm saying units because this could represent a general vector. It could be a displacement, a velocity, an acceleration. We would have the appropriate units on there. So if it were a velocity, our unit would be meters per second. Asteroid style, we would represent this vector according to its magnitude. That's the length of the arrow. We put absolute value signs around the vector to represent the magnitude. So the length here is 5 units, and the direction of it is given by this angle, 37 degrees above the x-axis. So in either case, we need 2 numbers to represent the vector. 2 components to represent A. We can write A as 4, 3, the AX component, the AY component, and have the units on there. Or we can represent A as 5 units, that's the magnitude, and then give the direction. At symbol, for 5 units at 37 degrees above the x-axis. This is your direction, this whole thing here, 37 degrees above the x-axis. That's piece of information 1, piece of information 2. 2 pieces of information here, 2 pieces of information here to represent a vector. Alright, so we got these 2 ways to represent it. Sometimes this is more useful, sometimes we want this, and we want to be able to convert between them. Let's look at that. First, how to convert from components into magnitude and direction. If we know the components of our vector, ax and ay, we can draw this triangle, right triangle, and then find the magnitude, which is the length of the hypotenuse, using the good old Pythagorean theorem. So ax squared plus ay squared square root, that'll give us the magnitude. Then we just need the direction. So we draw our triangle and pick an angle. We could have drawn a triangle this way. We could also have drawn it this way and found this angle instead. You can find either one. Usually the smaller of the two, sort of by default, is the one you want to go for. So now we need a little bit of trig. Recall your trig functions. We're going to be using them extensively from here on out. And we can say that tangent of this angle is AY over AX. And then using your calculator, we find the angle equals the arctangent. On your calculator, find the arctangent function and do arctan of the ratio AY over AX. That'll get you the value of this angle in degrees if you're in degree mode, or in radians if you're in radian mode. We should be in degree mode for now. But if you wanted to find this angle instead, tangent of that angle would be AX over AY. So they would be the arctangent of AX over AY. That would give you this angle right here. And of course that angle plus that angle should add up to 90 degrees. They're complementary. All right, that's how you would find the magnitude and the direction if you know the components. Let's look at the other way. Here we say how to break apart the vector into components. So if you know the magnitude and the direction, how do we break it apart into its components? How do we get the legs? Again, we'll use trig here. We know the magnitude, we know the length of the hypotenuse, and we know the angle. Sine of that angle would be AY over the hypotenuse. Cosine of that angle would be AX over the hypotenuse. So then if we want to solve for AY, this leg here, this component, we can say AY, multiply both sides by the hypotenuse here, by the magnitude of A, and then we get AY is the hypotenuse times sine theta. And likewise, to solve for AX here, we would multiply both sides by the magnitude of A and find that AX equals the magnitude of A times cosine theta.